Professor.
Okay. Today we will continue to discuss properties of Brownian motion or Wiener process, because as we have seen last time, it demonstrates more complicated behavior than smooth random curves. For example, last time we discussed the possibility for Wiener process on the fixed interval to have 2 points of global maxima, for example, like this. And we proved that such the probability that we will have 2 or more points of global maxima for Wiener process is equal to 0. So one can say that maybe such process demonstrate some complicated behavior. So today, what we will do, we will see some properties of Wiener trajectories, and then we will try to understand in which way we can describe these properties, how we can investigate it, and what we can expect to get finally. Let's start. I will start from the one-dimensional Wiener process. So let me recall that WT T is greater or equal than 0 is one-dimensional standard Wiener process if W from 0 is equal to 0, W T plus S minus WT is 0S, and it has independent increments. Of course, there exists a more sophisticated definition, and we also will use it. Just W is Gaussian process with 0 mean and covariance function, which is equal minima of arguments. So let us try to understand which properties this process has. First of all, let us discuss the roots of the Wiener process. Let us consider a sequence Wn plus 1 minus Wn, and I will consider a pair. Here is Wn. Then, if I consider such a sequence, I can see that that if we have here n, here n plus 1. Here we have Wn, and this difference will be opposite sign, like this one. Here Wn plus 1. Then for sure we will have a root on this interval. We will have a root on this interval. So let us think how many roots how many roots we will have using such argument. So let us consider this AN. It will be like Wn multiply Wn plus 1 is less than 0. Yes. In this case, we have the root on the interval n plus 1. So the question is, what is the probability that we will have the n infinitely often? We will have a n infinitely often. So let us check that this probability is equal to 1. Let us check that this probability is equal to 1. In order to do this, let us consider subsequence A to n. A to n. N is greater equals 1. Why I am considering this subsequence? Because you remember our covariance function. KTS for Wiener process is T minimum S. So if we take, for example, W n plus 1 multiply W to n and take expectation and divide by the 2n plus 1 2n square root. So I just am calculating the coefficient of correlation. Then what we will see, here we have 2n maybe, and here we also have 2n. So we have just like 1. But if I take here instead of 2, I take here 3 or bigger. Let it take 3n plus 1, 3n plus 1, 3n. Then okay, we also have 1. So I just want to obtain such subsequence in which the correlation will go to 0. So let's find it. Let us consider a time interval. Here will be our points. I just want to have a small correlation between these two things. So suppose here I have T1, here I have T2. Then what I need that T1 divided by square root of T2 and T1 tends to 0. So, okay, in this way, one can see that if if I will take a new sequence A, for example, n factorial, then this random events are almost independent. Now let us see that probability of n factor an, probability of an is equal to 1/2 because of the symmetry of the distribution Wn plus 1. I think. Let us check. This is a Gaussian vector. This is a Gaussian vector with a matrix n plus 1. N plus 1. Okay. Let's see. Will we have such kind of relationship? No, because this distribution is more or less concentrated here near the diagonal, but still we can expect that it will be positive. Of course, to ensure that this probability is greater or equal than some fixed positive number, we need to have another correlation matrix. So we already are in preparation for Borel-Cantelli lemma, but we still do not guarantee that probabilities of our events an are such that the series will diverge. So maybe we need to manage our to reconstruct our an. Okay. Again, put here T1, T2, and what we need to fix the probability that WT1 multiplied WT2 is less than 0. Then let us check the distribution of this Gaussian random vector. Gaussian random vector WT1, WT2 has 0 mean and covariance T1, 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 T2. So let's think. Let's think when we can move this pair T1, T2 in which way? Maybe if we can multiply this on the some number C, some positive number C, then nothing is changed. Of course, our vector will shrink, but this event does not depend on the multiplication on the C. So one can check that if we multiply our time parameters on the fixed number C, this event will not change its probability. So finally, we see that one can consider such kind. Instead of AN, one can consider B and which are equal to W. We see here multiplications, that 2n power, here W 2n plus 1 power less than 0, Then such event will have the same probability. Also, we see that if we take not all sequence, but take here a very rapidly increasing index, then we have independence. So we can see that this is constant, and just recall this. Finally, we get the following statement, that if we consider that our, for example, b(n) factorial infinitely often is probability is equal to 1. And what is the proof? We already see b(n) factorial are almost independent, and due to this sum of probabilities b(n) factorial is equal to 50. So we can use Borel-Cantelli lemma and get this one. Of course, this is just an idea, because almost independent, we have seen that it means that correlation disappears, but this is just some technical detail. The reason is, as I explained it to you, the constant probability here and independency of more or less increment of Wiener process on the long interval of time. So what we will prove? What we proved? What we proved? We proved the following: that trajectory of Wiener process have infinitely many roots on the our real life. So infinitely many roots on any interval C plus infinity. Of course, this seems not very surprising, because we remember that Wiener process, or process of Brownian motion, just modeling for us the random motion of the particle in the random medium. So it is expectable that this particle will hit zero a lot of times if we have one dimension of this. But now we will get a very surprising corollary from this thing. Namely, let us recall what we said about Gaussian processes. We said that if we have mean and covariance, then we define distribution of Gaussian process unique. So now let us define a new process, eta t, which will be equal 0 if t equal to 0. Then t multiply w of 1 over t when t is greater than 0. So I took new one process, and let us check its characteristics. We already understand that it is Gaussian process. Why? Because W is Gaussian. So the value of eta and W are Gaussian variables, are jointly Gaussian random variables. Now let us consider mean. Expectation of eta t, of course, equal to 0, because expectation of W is equal to 0. Now let's take expectation of eta t, eta s. To be more precise, I will think that this inequality holds. S is less or equal than t, then it's equal to ts. Here we have expectation of W 1 over t 1 over s, and it's equal to we know now that this 1 over t is less or equal than 1 over s, so it is equal ts multiplied or divided by t, and it is s, and it is minima s and t. So one can see that eta is Gaussian process, again with 0 mean and with covariance s minima t. So one can check that eta is new Wiener process, But see what happened with its roots. We just proved the following, that with probability 1, there exists a sequence. This is not a set of orders, but there exists a sequence say Tn tends to plus infinity, such that Wtn is equal to 0. This probability is equal to 1. Now, came back to here to this situation, and we will get that since that for eta we have that eta from 1 over Tn is equal to 0. Yes. So we can say that for our Wiener process, probability that there exists sequence, example Sn tending to 0 plus, such that Wsn is equal to 0, equal to 1. This is surprising thing. Let me try now to draw a picture. So we just consider one-dimensional Wiener process, and it occurs that the picture cannot be as follows. We must have a lot of roots near 0. In any interval which is close to 0, we must have roots of Wiener process. So, from this point of view, it is reasonable that we cannot draw a real picture of the Wiener process, just something which looks like. Yeah. So this is a surprising property of Wiener process. Also, let us check that a Wiener process does not have a good derivative. Actually, we already expect this. Yeah, with such a bad behavior with roots, it is expected that it has a bad property from the point of view of real analysis. Let us check that Wiener process cannot have continuous derivative, for example. In order to do this, I will fix interval 0, 1 for the time parameter, and I will consider such a sum from k equals 0 to n minus 1 gives a w k over n in square. So here delta w k over n, this is just difference, w k plus 1 over n minus w k over n. And it occurs that this, at least in square mean, goes to 1 when n tends to infinity. It is very easy to check. just recall that expectation of delta W k over n power 4 is equal to 3 k over n square. Oh, excuse me, not k, but 1 over n square. Because it is centered Gaussian random variable and its force moment is calculated very easy from the characteristic function. Then using this one and using independency of these increments for different case, it is easy to get this relationship. Now, let us imagine, let us suppose that W is from the space of C, C1, 0, 1. So it has continuous stochastic continuous derivative. Then, of course, such a sum from k equals 0 to n minus 1 delta W kn square can be rewritten as sum k equals 0 to n minus 1. Here we will have W theta k square 1 over n square. What I did, I just applied Lagrange theorem to any interval k and k plus 1n for continuously differential function. So just derivative. Then what will happen? This sum will go to 0. Yes, goes to 0 and the end tends to 50. This is contradiction with this. So one can understand that W has no continuous derivative. Really, it can be proved more general, but more complicated statement that was probability 1, any point W has no derivative at all. Without any statement about its continuity. It has no derivative at all at any point. So from this point of view, one can see that W is a complicated function from the point of view of real analysis. It has continuous trajectories. It has infinitely many roots in any neighborhood of 0. It has no derivative. So the trajectories of W have a complicated form. Now let's go to D, where D is a rate of equals to. The question is the following: how the trajectories of Wiener process looks like? For example, let's start from 0 and write some chaotic line. But you see, in this picture, I must to emphasize some common features for Wiener trajectories. But is it true that the picture is like follows? Like forward? Maybe no. because of we have a lot of roots in one-dimensional case, one can expect that maybe we will have an intersection in two-dimensional case. Maybe in three-dimensional case, we will have a complicated topological structure. For example, like this one, we will have some knots obtained from the Wiener trajectory. Yes. So now let us discuss the behavior of the Wiener trajectories in the case when the dimension of the space is bigger than one. First of all, let us discuss the following. Let us discuss the following thing in dimension 2. Let us prove that with positive probability we will have self-intersection. How can we prove this? How can we prove this? To think about this, I want to go back to the distribution of Gaussian vectors. Let me recall to you that we already discussed Gaussian vectors. For example, if we have this normally distributed random vector with zero mean and covariance matrix A, then if the determinant of A is greater than 0, we know that it has probability density, and this density is equal to the following expression of x is 1 over 2 pi determinant of A in n over 2. Yes. And oh, excuse me, just n over 2 here, and determinant of A in 1/2. Okay. Yes, and here we have exponent minus 1/2 A minus 1 x from x. This is density of our Gaussian vector. Now let us shift this vector on the fixed vector A. So let us consider new vector with the same matrix, but the new vector, new mean A. What will change? I will do these small changes just using just erase the previous one, and we will see that we have here x minus a, x minus a. From this point of view, one can see that the distribution of this vector and this vector are equivalent. And even one can define a density of this distribution with respect to this distribution. Let me write it. In order to get this density, I just must divide this expression on the same expression for first vector. What I will have? This constant will be cancelled, and here what will remain? Let us write it. So we have a density Q of x, which will be equal to exponent here a minus 1 x a minus 1/2 of a minus 1 a. So we can again we can say that the distribution of the shifted Gaussian vector is absolutely continuous with respect to distribution of initial Gaussian vector with the following density. Now I want to do the same for distribution of the Wiener process. I will do this for one-dimensional Wiener process, but for multidimensional, the formulas remains to be more or less the same. So what we will do? We already know that if we consider Wt on the interval time interval 0, we will get a random continuous process. So I can say that W now is a random element in C01. You see, more or less the same. C01 exactly is finite dimensional Euclid space, is Banach space. And of course, this is Gaussian random element in this space. So one can expect that when I will shift W on some vector, some function, I will get equivalent distributed random element, exactly as here. More or less it happened, but we must be careful because it is infinite dimensional case. Let's try. So I will consider Wt plus Ft. Instead of Wt, this is my shift. This A. This is my shift. But I will suppose that F has some additional properties. I will suppose that F has some additional properties. Namely, f from 0 is equal to 0. And f belongs to C1, 0. Actually, it is natural even from the common point of view, because we already know that W has ugly trajectories. So when we will shift it, it is not convenient to add again something bad. We just add something smooth to W in order to keep these bad properties. So let us consider this one. And now I will check the so-called finite dimensional distribution of the new processes. So I consider W plus F, and I will take T1, okay, which is greater than 0, less than Tn, less than 1. And I will consider distribution of this random vector. In order to do this, let us consider firstly density of W T1, W T. It is a well-known formula, so I just write it. P of x will be equal to the product from k equal 0 to n minus 1 over square root tk plus 1 minus tk, and here is exponent, and here minus 1/2 divided tk plus 1 minus tk, and maybe here xk plus 1 minus xk square. Okay, here I use such a notation. This is a good representation for density of the distribution for finite number of values of Wiener process, and it is evident from where I get this formula. I just use the independence of the increments of Wiener process, because everywhere when we say independence, we have a product, and this is evidently the distribution or the density of the increment. So we have such a Px, and now let us consider the new density which is related to Wt1 plus Ft1 Wtn plus Ftn. Then what we will have, Px, Pfx will be equal to product from k 0 to n minus 1, 1 over square root tk plus 1 minus tk, and here we have exponent this fraction 2tk plus 1 minus tk, and here xk plus 1 minus xk plus f tk minus f tk plus 1 in square. Okay. So one can see that for our two vectors, this one and this one, we have probability densities, and now it is easy to understand that they are absolutely continuous mutually, and one can find the density, the ratio of these densities. So one can find the density of this vector with respect to this vector. And this density Q, I will write it from W, because you remember X, actually this is WT1, WT. So let me write it from W. It will be exponent. We already know that this preliminary constants will be cancelled. And here we have the sum from k equals 0 to n minus 1. Here delta W, delta F, tk, delta W, tk, and minus 1/2. Here we have sum k0 n minus 1, delta f tk square. Okay. Only we need to put here the limits here and here, delta tk and delta tk. That's all. Okay. Now it is. So we have such a formula, and what happened if we will increase the partition tk? The last formula, it's easy to investigate. This is the exercise from the real analysis. Just the sum delta f tk, delta tk and here is square. We again can use Lagrange theorem. 1 tk will be cancelled, and it will go to the integral from 0 to 1 f prime t squared when our partition will. This also goes to some integral. This also will go to some integral, namely the sum from k equals 0 to n minus 1 delta f tk delta w tk over delta tk. I will again use Lagrange theorem. Then what will happen? It will be equal to sum from k equals 0 to n minus 1, and here is f prime to the k delta W and K. So it remains a Riemannian sum for Stieltjes integral with respect to W, but we already know that W is a function which has no derivative. It is a function of unbounded variation, but still in two sense, in square mean, the sum converges to the subject which we call stochastic integral. It is known that in this case it converges to some integral f prime s dws. From this point of view, one can see that what we will have, we can shift our Wiener process on the smooth function and get absolutely continuous distribution. This will be a good idea to investigate distribution of Wiener process in the space C01. For example, we will have the following lemma. For all h belongs C0, 01. This 0 means that h from 0 is equal to 0. For all epsilon greater than 0, probability the W as a random function belongs to the pole with the center of H in radius epsilon is positive. So we live in any ball from C01 with positive probability. This is interesting consequence of our previous consideration. What does it mean? It means that that if we take any smooth function and take the small corridor near, then with positive probability, Wiener trajectory will live in this corridor. From this point of view, it will be more or less evident how to discuss geometric properties of Wiener trajectories. We will do this next time. Also, we will prove this lemma. Now, this is all for today. Thank you for.
Oh, thank you, Professor. So take care. Oh, thank you, Professor. So
thank you for attention.
Okay.
So,
take care.
Maybe some questions?
Yeah. So
maybe some question?
No question. So thank you today.